Hi all, how are you doing? It's nice to see you again. Although I don't see you, of course, but I feel you. So yeah, um, today I wanted to have a stream about the topics I'm working right now on. I'm working on those topics for my book, and therefore I'm very interested in discussing them because they are in my everyday programming life, and therefore I decided to make another talk, not really a talk but a stream with my experience with type level programming in Haskell. I did one previously. This will be another one, and this one will be focused on type level evaluation models. Evaluation models in general, it's something that we can run, and those models can do interesting stuff for us. Many of well-known evaluation models, such as Turing machine, lambda calculus, or maybe some imperative scripting, something like that, they are Turing complete. And the name Turing machine and Turing completeness, those two names are not coincidentally similar. It's the fact that if some model is Turing complete, it means that you can implement a Turing machine in that model. And the latter means this model can do evaluations which are evaluable, which are in principle can be evaluated. For example, integer arithmetics can be evaluated. Strings and operations over strings can be evaluated. Calculating some functions can be evaluated, and a lot of many things we can evaluate. Most of our languages are Turing complete. This is where we can have arithmetics. We can add numbers. We can multiply what we want. We can call functions from other functions. We can define variables, and etc. and etc. etc. And everything boils down to the idea of evaluation. This is a computer science topic. I'm not particularly strong in this topic, but if you have a Turing complete system, this means you can program Turing machine, you can program lambda calculus, you can program other Turing complete systems, for example, game of life cellular automaton, and those things will be kind of equivalent in their strength of evaluating things. Certainly our programming languages have more than just some evaluation model. They need to work with the user, with the input and output, with the external services and subsystems, and therefore input output is another extra feature of our programming languages. And we can even have a programming language that is simply some Turing machine plus input output possibilities. This will be enough for doing the stuff we are doing in other languages, in theory, of course, because using such a primitive language will not be a very pleasant experience. You may remember about brainfuck. It's a Turing complete language. It has maybe 10 operations, something like that. And those operations look like increment, decrement, shifting, and some other things. And you can there are input possibilities to type something and output possibilities to print something. In theory, this language is very powerful. it can do what other languages can do, but in practice you won't be happy using that language. Yeah, so we do many things with our programming languages, and sometimes we are interested in programming evaluation models in our languages for some business purposes. In this particular case, I implemented 3 evaluation models in my for my book. Those are Turing machine. Turing machine here is just an example that you can do that. Also, I implemented a very weak and not very powerful lambda calculus. There are many different lambda calculi. Those are even typed and untyped models, and they very different in their not purpose but properties. Typed lambda calculus can be implemented in different ways, and this is a really deep topic. I am not an expert at all, and even more, I am not an expert in lambda calculus itself. But sometimes when programming in pure languages, you feel this need, because sometimes you need to kind of encode an operation and pass a result of that operation into other operations. You need some sequencing, not just effects, I would say, effects on pure values. So when you need sequencing, you immediately face a problem how to encode that sequencing between one operation and another operation, and lambda calculus, or maybe its small part lambdas, can solve that. You have an operation, it gets some input values, it calculates something, and its result can be passed into the next operation if that operation is enclosed by lambda. You enclose it by lambda. This lambda takes input parameters, and the results from the first operation go into the input parameters of that lambda and the operation itself. So this can be a very needed feature if you program in pure languages. Functional programming is like that. You need to call some functions and pass their results into other functions. But also type-level programming is often can be seen like a pure functional programming. This is true for templates in C++. It's not the whole truth, of course. C++ templates are much wider than just pure functional programming, but still you can do that. And it's more or less true for Haskell type level system. Haskell type system, I would say. And sometimes encoding specific domains means you also need those evaluation models. Yes, the question is, why should you even do that on the level of types? Why you can't just go with regular value level solutions? I will not give you some motivation about it, because it's another topic. We can talk about that. Feel free to ask questions. Let's have it as granted that today we are operating with types, and we work on the level of types exclusively. So first, let me present you the Turing machine application. This is a demo application, and it is naturally just a Turing machine implemented as an application that you can feed with types and encode some rules, and those rules will be evaluated against the types and types. Yeah. Let me first, well, I probably won't be running this application, but you can. This is the repo of my book. You can, and this application has several purposes. First, it demonstrates type-level programming. Second, it demonstrates the difference between type classes and free monads as interfaces, and discusses the implications of using one or another, and what this means for the application architecture. So the application is not that big, although it has several actions that you can evaluate with that. Let me show you those commands. Commands. It allows you to create tapes. Tape is simply a string, some chars, some characters of that string, and the rules can work with that tape. You can load tapes, you can load predefined tapes that I created for you. You can load predefined rules, this one, or you can load rules from a text representation from the outside of the program. This means it's very easy to parse tapes, right? It's just a string, but parsing rules is not that easy. You need a parser, you need some form of translator from the parsed structures to the valuable structures, but it can be done. So this is a showcase on how to make rules, serializable rules. There are other commands, and one of them is certainly run a tape and a rule, and the tape will be processed by that rule. Let me show you samples. For example, this is one. It's a model, it's not a sample. I have assets and binary increment. For example, it's a simple rule solely declared on the level of types in Haskell. It essentially shows how to encode arithmetics with Turing machine. It treats Turing machine as a state machine and can have many states. For example, we have 6 states. Those states represent some graph of operations. Let me show you the graph itself. Here it is. And I believe you're familiar with the idea of graphs and state machines, because Turing machine is a state machine, right? State machines can be a more wider topic than Turing machine. They can do much more than Turing machines do. Yet this one, it simply matches the current string. For example, we start from the first state. It matches the current string, the current character under the head of the machine, and depending on what it reads, it goes either one direction or another direction and does several actions. For example, we got 0, and what we should do, we should skip this specific cell under the head and move the head right and go to the second state. And again, we can do that, and we therefore analyze the string of integers and apply some rules, rewriting rules. And this is another evaluation model, actually. Rewriting rules, string rewriting rules can be Turing complete. For example, in C++, there are macroses which are rewriting rules, and if I am not mistaken, you can correct me, they are Turing complete. So we can, again, as I said, we can match some symbols and evaluate some actions and proceed with another state. and that state does own matches and does own rules, like writing another symbol into the current cell, going left and proceeding with another state. And doing so, this doesn't look like a plus operation, right? It doesn't look like that at all. It's a Turing machine representation of a summation operation, well, increment operation. What a tape can look like, for example. Do I have a tape? Do I actually have a tape? Probably in tests. Probably in tests. Yeah, those are simple tapes with just two symbols. Well, yes, this one. A tape is a string, and binary increment is a rule, and we can run one against another. If we have this tape, then we get this tape, and etc. So this is the whole idea. It's difficult to see how we can evaluate everything from this, right? Because our programming languages are very concise. They have special syntax and many levels of abstraction, and operating by those languages, we can skip many steps that are needed here. Yes, Turing machines are fully capable, but programming them is not very pleasant because you need to do a lot of stuff. Well, let's move to the code itself, because I wanted to show you the code. I probably won't be writing any code today, but anyway, this is a type level programming in Haskell. Well, actually, this looks like a model, just a model with algebraic data types, right? Those types are not simple because they are parameterized. They have some parameter. This time it's level, and this level parameter will indicate on what level of code we use this structure, because this one is just a regular algebraic data type. We can create values of that data type. For example, custom my custom rule. It will be custom rule value level, and I can do regular stuff. For example, I can create rule with rule name my rule, and with initial state 1 and empty states. For example, this is just a value level code. It doesn't do anything on the type level. It just takes my value with this specific type, nothing else. But what we've seen here is a type level. It's, let me move it into that, and for easy comparison, it's not binary increment is not a function, is not a value like here. It's a type, and everything here is type. A rule is type. Here it's a value constructor, and here it's a type constructor, and it works with type level, not with value level. And the syntax difference also important here. This one indicates that we will be working with not the custom rule itself, but with its promoted value, with its promoted type level value, I would say. So what can be sorry, I'm a little bit confused. Do we have something in chat? OBS has crashed when I clicked to it to verify. Alright, so let me continue explaining what's happening here. It's I'm not sure how deep I should go, but I just want to explain it. So we are programming with types. Everything is type here. It's a type, this is a type, and state is a type. and those types can be obtained from the same model, from this model, custom rule, custom state. They can be obtained with a specific Haskell extension known as data kinds. It's a unique idea in Haskell, I believe. What we get is, when we have a custom type, we also implicitly get this type level representation. It will be in our code. It will be available for using. There will be a rule instead of a rule value constructor. It will be a rule type with parameters instead of fields. Again, it was a algebraic data type with this value constructor, and now it becomes a rule type, I mean kind. It becomes kind, and this becomes a type. Specific Haskell type level notions. I've been talking about this type level promotion and the related design patterns in another stream. Today it will probably be shorter in terms of what happens here, but it's a type level representation and can be only processed with specific type level compiler in operation. It can be traversed, everything can be traversed at compile time. I do that with so-called static materialization. It's my personal term. I know you can use another term. Let me open language materialization. This can be this type representation can be traversed with static materialization. I have type classes for that. Type classes can work with specific types that should be at the type level. It's a specific design pattern. It doesn't need it in general, but for my purposes it works well. Instances of this type class will be able to construct and reconstruct types at compile time. For example, like here, we need to pattern match over the rule. It's a type with several type parameters. We pattern match over it and do related stuff at runtime. So we pattern match at compile time and do stuff at runtime. We connect two worlds and evaluate, or maybe construct some value representation of the Turing machine and evaluate it later. In this particular case, we just converted from the type representation to value representation. This is how we reconstruct lists. We won't be learning the details because type level in Haskell is cryptic and difficult. Yeah. Anyway, this was a business task. Implementing a Turing machine and application was a business task. It wasn't for something. I don't use Turing machine or its rules for anything but demonstration. However, I have another application which is about, initially it's about a roguelike game. We had a stream about that previously. It's about a roguelike game with world that can be set up on the type level. World and objects and items can be specified on the level of types. Let me open some examples. And for this to happen, I was needed some object-oriented model, which is also an evaluation model, just implemented in Haskell on the level of types. and it has this again the same idea, the same design of type level programming, and everything here is type. It can be traversed on the type level. In this particular case, we have some specific need for that. We can have object-oriented programming fully operational and type safe. We can have abstracted interfaces, or for example abstract properties, and we can have specific properties and or classes if we wish, that will be deriving values and fields from the abstract properties objects. So if we have an abstract door with 1, 2, 3, 4, 5 fields, then a specific door will derive those fields, and it can modify those fields, because in OOP overriding what comes with the abstract parent is a common practice, right? So we can override that. But it's not what I wanted to tell you about, because we had a stream about type level programming and the OOP for the game The Rock. I wanted to talk about scripting. This scripting is essentially an imperative scripting on the level of types. This model allows you to write real scripts, and the possibilities are not that rich, because you just need to program extra features of that scripting language. But for now you can read fields, write fields, for example write data to field having this path inside your graph of properties. You can address special property, even nested one, even that one that is referenced indirectly. You can write data into that field, and you can read data for writing from another source. In this case it's a constant. You can read constants of predefined values. In this case we write a field of paths here in the terms of this domain model is a list of breadcrumbs from one property to another property to a field. All those things are named. They have a specific key associated with each node, each step, and path is a breadcrumbs to the final target that we need to change. In this case we need to change the state field of the script, of the property that has this script nested. And let's take a look at this state field. Do we have this field in this abstract door property? There is a script, right? That's a script. We assign this script to the abstract door. We can have many of them because it's a list. You can consider those scripts as methods essentially. Object-oriented programming is data plus methods, and scripts play the role of methods here. So state, do we have that? Yes, we have this field here. The field is a key and value, like in Python. I use the model of OOP not from Java and not from C++, but probably from Python with its dictionaries as classes, and maybe JavaScript with its idea of prototype object orientation. So it's close to that. And the field state has a value inside. This value can be modified. So this is what the script does. If triggered, it will change close state ref to open state ref. Doing so, we have an imperative model. We can have many write operations. We can have read operations, although read is just a reverse of write in this sense, because read will have two parameters, read data, two parameters that are inverse of the read operation, read from to. So they are actually the same operation. You know, there is one more evaluation model which is super simple. This evaluation model is known as the move assembly operator. Move instruction that takes a value from some place and writes this value into another place. It's proven that the move assembly operator instruction is Turing complete, and you have a whole program built essentially from the move operators. There is even move fuscator program that turns every executable file into a list of a huge list of move operators, solely move operators. So this is an evaluation model. There is one more interesting evaluation model that has only one operation in it, the so-called YOT operator, or maybe combinator, but I probably won't talk about that yet. So yes, this is how I implement an imperative system model inside the type level programming. And it also has some nice feature. It's type safe. So if we have a field of paths, for example, we can only write it having a path variable or constant. It will prevent you from writing wrong things. This is better shown on the Zeppelrock application itself, because the model there is more developed, and I would like to talk about that. Close folder, Zeppelrock. I probably need to demonstrate some specific. Yeah, it's actually the same data, just a separate application and a little bit more developed model. You can see again script with list of operations. Let's dive into the code itself, because there are several very tricky things I probably want to mention. Model, script, and also we will need common. Let me start from the maybe custom script algebraic data type. This denotes a script in general, and script can have name, and script essentially is a list of operations. Those are not returning operations, they just like effects. Those effects can be done over some properties. They can mutate properties and can write data from to and from values. And script operations are free essentially operations right now. We can create more. For example, every model needs a condition operator, if, or maybe case construction, a switch, a branch that could be used to select some condition, select some operation depending on the condition. This is essential. It's very important for every evaluation model, and it's not difficult to create. Just had no chance, but we can imagine what it could look like. It could be conditional. For example, it can be conditional. It should take a source a source that will have some boolean value inside, and I can specify explicitly that I need a boolean value. Bool tag, it will be a source with bool value on the level of types. Yes, I don't need parentheses here. And if this holds, I need to evaluate another operation. So here we have script op lvl, and that's probably it. Maybe even a list of those operations, maybe even a subsequent script, which will be even better. We can merge different scripts without merging their operators. So we can have custom script lvl here. This is for success case, and we are working with functional programming, right? In functional programming, everything is an expression, so it should be if then else. We have if then, now we should have else. Custom script lvl. This will be enough for having a conditional operator. Failure case. Failure case. And there should be some code that understands what I just wrote. I need to write materialization, I need to write instantiation, invocation, but anyway, this is not difficult considering the methodology I created for type-level programming. The problem with Haskell's type-level programming is that everyone does this differently. You can open particularly any type-level library, or even just simply any library on Haskell, and you will see how many type-level bits are there. Folks really love playing with Haskell and with type-level programming, and they love implementing various math models such as category theory, abstract algebra. They love exploring type-level features. The problem is that the code is often a mind dump of a specific developer. So you need to understand how the developer thinks in order to understand the ideas and approaches taken in the code. And more often it's done without a system, just intuitively. I want to distance from this way of programming. With my book and with my code, I want to show that you don't need all the features on the level of types, even in Haskell. Haskell is super rich in this term, in this way, in this sense. It has dozens and dozens extra extensions like those ones. GHC has those extensions, and combination of those extensions is an explosion of possibilities. Not all of them are even known. There are dark places. No one has ever been there. No one there. I believe there are different combinations of the type-level features that developers didn't yet think about, haven't a chance to try, and maybe there are consistencies or inconsistencies in combining those type-level things, a lot of them, and the surface of exploring is super rich. This is why it's a problem. It's a huge problem. You don't really know how to do stuff, how to properly encode type-level models so that other developers could work with it, because they need to spend time understanding what you just wrote how it works and why it's so. So my idea is to provide a methodology, and it has four specific design principles. Let me name those principles. I'll try to name them using my memory, but maybe first, dumb but uniform. This principle means you need only a small set of features to achieve very impressive things, to be able to make very impressive things. You don't need the whole set of features. Why? Because even with this small set of features, some emergence can be achieved. Emergence when you can program complex systems out of simple rules. For example, cellular automata, especially in Game of Life, is an emergent system. There are 2 or maybe 3 rules of a Game of Life cellular automaton, and the worlds you can produce with those simple rules are just mind-blowing. The fact that this cellular automata is Turing complete proves that. Not only, but yes. So simple rules, complex implications. This is called emergency. Same for type-level programming. Type-level programming is emergent. Simple set of operations to do stuff. Simple set of operations to do stuff. A lot of domains you can cover with that. Second, no perfectionism. Of course, everything can be polished and polished and polished. There is no limit. This process is infinite, and everything can be done even more and more mathematical if using types, but there should be some threshold or maybe some critical point after which going further doesn't make sense, because it increases accidental complexity of the code. Type-level programming is very complex and it brings a lot of accidental complexity. So you would have some imperfect yet enough system to do stuff. And what else? Let me memorize those principles because I forgot. Oh, sorry. Let me open my book and I'll find those principles. Yeah. Principles. Where are you, principles? Where are you? Come on, it's the first chapter, available for free reading on LeanPub. Yeah, I found them. Occam's razor. So you don't need to invent new shiny terms just to make everything looking smart. This is very important, and this helps to keep the code understandable for others. For example, you don't need to attract mathematical terms. It's actually not needed. All those isomorphisms, bijections, categories, and etc. In Haskell, folks love using this terminology, but actually it's not needed at all. You can name everything, literally everything, using the common and well-known terms. You don't need to name everything after mathematical terms. It might be useful for writing papers, or maybe inventing some libraries and making proofs of concepts, researching computer science, but not for real development. This should be avoided, and therefore comes rather. I truly believe that you don't need math to program with types. I was told that I should not even try writing book like that if I don't know math or can't operate with math terms, because they essentially see programming with types as a math exercise, and it can be because we have formal verification area, and in that regard, everything we write on the level of types is a proof, right? Or how they say it's a theorem and the code is a proof, if I am not mistaken. This is an interesting point of view. It's just not about pragmatism, because it costs a lot. You cannot convert the type system into a very useful theorem prover, because you need a very specific environment for this to work, and you need a very specific domain for this to work. Most of domains in our world, in industry, do not require proving something. They require to program some dirty things, and that's all. They require to achieve some result. Aesthetic Vibes is writing hi. Hello, good to see you. So those are 4 general principles I use and recommend using to sanely program with types, and the methodology I am describing in the book explains how to use this style of programming to achieve what we want to achieve. There are design patterns associated with this style of programming. For example, this one is a granular type selector design pattern. There is static materialization and dynamic instantiation compilation phases, and those things can be designed by an example, not here, just in those things can be designed by an example without diving too deep into what's happening here. If you know the pattern, how to process things on the level of types, you will be able to solve your problems, to program what you want. And dynamic it's static materialization. It converts from type level representation to value level and mixed level representations. Dynamic instantiation can convert what it gets on the materialization phase into something working. Again, this can be programmed according to the design pattern, but also it requires some creativity, I would say. So yeah, static materialization is completely turned into a pattern, and dynamic instantiation is dependent on what you want to achieve. So this is a methodology, and the example demonstrates that. By the way, I was talking about imperative programming, right? We have targets and sources here, and extra features to make those things type safe. What means type safe? If you read a target that has some variable inside, then you can write that variable into an appropriate place only if that place matches by its type. For example, you can read a boolean variable into boolean field and vice versa, but you cannot read a boolean field and write into string field. You cannot without conversion, at least, right? Explicit conversion. And you need to program that on the level of types, and organizing values and variables is a big pain in this sense, because values essentially can be of any type. Values are not only booleans, are not only integer strings, they also can be user-defined types, pairs of something, for example, pairs of two strings, or maybe a user data structure, or maybe account from a bank. Those are user-defined types. And making your type level model working with those unknown types, unknown upfront, is not an easy task. It's not an easy task in programming language design, and it isn't in type level programming, because all you can do is to program some generic approach to those values and make this generic approach support future coming types, make it future proof. I achieved this by having a specific construct. It's not an easy construction, but it works. I had many hours of experimenting to find some model that works okay, is not super complex but complex anyway, and can have a good user experience. We've seen here that we can read and write. I also can declare variable. I need to specify this variable. For example, my bool var. Yes, I need to hint myself on what this variable should look like, because I don't really remember. Its values, its values. I need variable generic var def blah blah. For example, bool var name and initial value. Bool var my bool and initial value true. This can be also prefixed with a tick. This indicates that they are type level. Those also can be with ticks, just omitted. It's allowed to omit those ticks. Sometimes the compiler in Haskell gets confused, so maybe we'd better to put those ticks here. So I can now declare variable my bool var. Is this the correct syntax? Declare variable, the target source script operation declare var. Yes, it's correct. It's a correct script. And then I can write data to field. This is specificity proxy I need for some inner workings. I could not get rid of that. My bool var to variable, of course, to var, and this to var. Yes, it doesn't need proxy. All right, and from for example, from constant. This constant is a different type, and this won't compile because bool variables, they are bool and defined like this, and path constants, they are not bool. And I need several type level tricks to make this happen. All those vars variables, they are tagged, they have a tag. I invent type level type system. So there is a type system itself in Haskell, and I invent one more type system above that. And those tags must be equal for methods from var and methods to something, to var, from field to field, from const. And I achieved that by requesting the same tags on for the write var instruction. But this is not this is not everything. Actually, it requires a lot of type level tricks to make it work. Especially those are wrappers, right? And especially in materialization, because in Haskell type-level programming can be intimidating, and working with those variables finally demonstrates. Let me open. Yeah, well, actually I won't explain what's happening here. This is again instances of materialization type class that I convert variables into value level representation. Yeah, I had to find a design that would work and would have some convenient developer experience, because I can declare variables of different types now and tag them. For example, string value is another part of the variable feature, but let me open it. Yeah, generic value definition. Again, it's tagged, and those tags can be extended, and those tags look like type level strings. They can be regular, they can be compound, for example, for int of pair, and they indicate the type of variable of value and do not allow us to mix invalid types and invalid values. Yeah, and I can extend this system. I can have a user-defined type if I need to. For that I would add one more tag, and would think of how I want to represent that type and provide specific type level value constructors, smart constructors for that, and also obey several type level interfaces and etc, etc. So yes, this is a huge problem actually. Yeah, as you can see, a lot of code. So yes, this is how I solve the problem of imperative type level programming. There is one more model I want to show you. It's about lambda calculus, or maybe it's Sorry, OBS has crashed again. It's a shame actually. It gets crashing on my Linux machine, but the whole code is here on my Linux. But anyway, there is one more model, evaluation model, that I want to share with you. It's a lambda calculus on the level of types, or maybe it's simple representation, simple lambda calculus. There is the application for showcasing that model, and also for showcasing a real extensibility in Haskell done with type level programming. Real extensibility, what I mean, you can declare specific bits and even have them completely separate from the main core, from the main functionality, and it will be it will work like a plugin system with types. So yes, it can be used for a good extensibility, and also kind of solving the so-called expression problem. So let me first show you the example. I need to open some spec. Yes, this program is about making auctions. I tried to implement a model for encoding any possible auction. There are various auctions. I'm not sure, do I pronounce it correctly? Auction, maybe auction, right? For example, English auction. There are lots. They can have some predefined value, or maybe can be only available in some currencies for some states. This depends. Different auctions have own ways of defining lots and who is eligible for participating. Anyway, I can define lots, and I can define the flow of auction, who to ask, who will post a bond, who will how to say, request something, who will post a price that they want to pay for that lot, and etc. Different auctions have different flows, so I need some model to show this flow or customize it for specific need. This is where I implemented this model. I can have actions that also work with mutable values and can print them, by the way. I can stack actions. It's not a list, it's a nested functions, I would say, because well, those actions do not return anything, but I have lambdas that will return anything, and I can stack them into a type level list in forms of nested actions. And those actions work on those lots and corresponding values. What we can show here, for example, an action for an English auction. This action gets a lot name and passes it into a nested operation. So I kind of combine operations. I suppose this is a lambda that accepts one parameter. It's not a syntax of lambda, right? You don't see here something like that. It's not needed actually, because if we consider this a function, then partially applied like here can be filled with some value. We just pass it as a third parameter in this case. Well, it's a little bit more complicated, but yes, those things are functions, and those things are lambdas. Print is also a lambda that accepts some parameter. In this case, it accepts string. So concat gets a string, combines it with the predefined string, and then calls another lambda and passes the result to print. So this is how I can encode lambda calculus or something like that on the level of types, and it uses a different implementation model, different methodology, I would say. Well, actually the methodology is quite the same, just another approach of declaring the models, type level models. Let me open. Previously it were algebraic data types that were promoted to the level of types. For now, it's empty algebraic data types. They don't have value constructors. They only have type parameters that I treat as fields. And I don't need promotion here. And those empty data types represent domain notions. I have some machinery to make this work. For example, those are, well, I'm still working on the naming, so those ticks will be replaced by implementation, and maybe I have something more represent, well, maybe not. So yes, those are implementations. I mean specific value types on the level of types, and I can pass interfaces. For now they called lambda tag. Here it's an interface for lambda and for here too, but actually they are type level interfaces. So I have specific shape for those models that you can combine and get a complex model out of simple, not very simple, but yet more or less simple bits. Those are extension points. extensible places, and those are interfaces on the level of types. I can add more manies, for example, without recompiling the core. This is the core, and extra money can come in the test. For example, I have what do I have for extra extensive? What do I extend? I add more monies. All right, more currencies. What else? Yes, I defined some specific instances for that. Won't be diving too deep because all the things are specific to this domain. What else? This is introspection. Introspection means traversing the types and analyzing them. You can, for example, print the whole domain model into a list of strings. I'm afraid if I switch the application, the OBS will crash. Maybe I can run a terminal from here, and we can see how this works actually, right? Let's see. Something is modified. I hope this won't break. Stack test. Let me open AuxSpec. I want to show you the flow that I get when run. I have tests, and there is a auction model, right? English auction. It gets some lots and then starts evaluating. And for example, it posts a lot number 101 and does some description and accepts bits, accepts currencies, and etc. etc. This is an introspection of that process. Once you have a type level representation, all the operations are available for your traversing of the types. Because when you have a regular code, for example, like this, you cannot traverse the code without evaluating it. You can't, because functions need to be called. They want arguments. Those arguments are not available at the compilation phase, and it's not clear how to say this is a function. Look, it accepts such and such argument. You cannot print functions, right? You cannot. They are not a printable item. But once you have type level evaluation model like this or that, you can finally introspect each part of it, even if it's a lambda that does something, even if it's a imperative script. You can traverse it and inspect every possible bit of the type level model. You can print it, you can serialize it, you can generate models on other languages at the compilation phase, and you can do other things that are not generally available for a regular code, right? This is a ready model for being serialized into a file and maybe loaded into, for example, JavaScript. Doing the opposite is more difficult because constructing types from values is not easy. It requires dependent typing, and this is what happens when you parse something into your program. You have a string value representation, right? A string, for example, data from HTTP or data from console, and you cannot simply take it as your new data in your program. You need to parse it, but to parse it you need to correspond each value to a specific type, which is a direction of interpreting that is not simple, because when you run a program and get this string, types are generally not available. Types are get vanished after compilation. So this is where dependent types are used, and parsing is quite often related to dependent typing topic, if I'm not mistaken. Correct me if I'm wrong. So this direction is very difficult, but the other direction can be done easily with types. Not easily, you need to do type-level programming, but still, you cannot serialize regular functions, right? But you can serialize types. So this is what I wanted to share with you. Maybe I missed some ideas. Yeah, I won't go into the details on how this particular model works, how to define your methods, how to define your flows, but I would say that auction can have flow, meaning what to do and how to do with lots, and how to interact with the clients, with rich people who want to buy something. And those operations, flow operations, they can be provided as extensions to this model. They should not exist encoded directly. They can be provided later. For example, I have several extensions here, like allowed countries, not actions, but maybe actions too. Well, maybe not actions, but I can provide specific actions. For example, some auction wants not only say a lot, but also wants to report the result of this auction to some external others. So it can have an action that can be embedded into the flow, like here, some specific action. Instead of readref, it can embed another action, report something, right? Report bid is closed, for example, like something like that. And maybe some pass data, maybe read some reference and pass the internals, what the lot and what the price and etc, etc. This report method can be added without recompilation of the main auction mechanism. So this is an extensibility. Well, that's probably it. The details are very difficult, but I hope my book will be more or less accessible to many. I think Haskell developers won't be much interested in that, because they I believe they know everything, and they don't need such books because they are experts already. But maybe some Haskellers will be interested to read a great stuff and a good writing, and very accessible writing, not academic one, very pragmatic. So that's it. Thank you for your attention, and see you next time. Bye.